So let's move now to the second speaker. So we discuss now about reinforcement in digital fabrication. So the second speaker is David Wang, that is going to present the presentation entitled Use of AR Glass Textile as Reinforcement of 3D Printed Concrete Components. Dr. Wang is a postdoctoral researcher in structural engineering within the School of Architecture, Building and Civil Engineering at Loughborough University, UK. He's currently working on the structural design and modeling of unreinforced and reinforced 3D printing concrete structure. It is supported by 2 UK EPSRC projects. So welcome, David.
Hello, everyone. Thank you for this invitation. Today, I'm going to present our research on the use of AR glass textile as reinforcement of a 3D printed concrete component. One of the most challenging part for 3D printing concrete is the reinforcement. It's a bit challenging. There are several reinforcement methods have been proposed. I have listed several examples. The first one, as we can see from the top left, is external reinforcement. So after the concrete is printed, we will use some post-tensioning or something to place all the printed segment all together. And also we can try to place some metal cable reinforcement inside the concrete bead. And also for we can also print using 3D concrete printing technique to print concrete formwork. And in this case, we are able to place the steel reinforcement or other kind of reinforcement inside, and then we can cast the concrete later. But if we are going to let's see this example. So Loughborough University printed this doubly curved facade 10 years ago. But when we did it, we didn't have any, or didn't place any reinforcement inside. So if we are trying to place any reinforcement for this facade, which will be used in real practice, it will be very difficult at this stage. So the reinforcement strategy should be proposed for very complex, the doubly curved thin-shelled element. So we came up with the idea of using textile reinforced concrete for the very complex geometry 3D printed concrete structures. The textile reinforced concrete has several advantages, which includes full flexibility in architectural design and high reinforcement efficiency, and also it is very suitable for curved, complex geometry thin-shells element. I would like to have a very preliminary brief comparisons between the textile and the steel. For steel, it has corrosion problems, and the yield strength, as we can see from this figure, so the yield strength for the mild steel is usually less than 400 megapascal, and even for the high yield, for the steel with high yield stress, the yielding stress is usually less than 500 megapascal. It's heavy. It's around 8,000 kilogram per meter square. But it is very ductile material. So from these figures, we cannot see how ductile the steel is. Actually, the rupture strain for the steel is about 20%. Steel lacks the shape's flexibility. Let's go to the textile. Textile is made of carbon or glass or basalt. There's different kinds of fibers we can use. So all kinds of textiles are very durable. So it means that we can try to reduce the cover thickness. This is especially competitive when we are trying to reinforce thin-shelled concrete element. It has a very high tensile strength. In our study, we are going to use glass fiber. So we can see from this figure, so the E-glass fibers has a tensile strength, which is more than 2000 megapascal, which is much higher than the steel. And also it is very lightweight. It is 1/3 to 1/4 the weight of the steel. And but the textile does have some limitations. It is very brittle. So if we are using the textile to reinforce the concrete members or the concrete structures, we need to be very careful to prevent the brittle rupture. Textile is very flexible, so it can be made into very complex geometries, which can fit very well with the thin-shelled curved concrete element. So we designed an experimental program to see how the textile can, to what extent the textile can reinforce the concrete members. The details of the beams has a relatively smaller size, which is 450 in length, 100 millimeter in width, and 20 millimeter in thickness. The reason why we choose such a thin section is we are trying to apply the textile into thin-shell concrete members. And we use the different number of textiles in our samples. You can see from this figure, so we have 1 layer, 2 layer, and 3 layers. And between each layer of the textile, the spacing is 5 millimeter. In addition to the number of textiles, we also compared the difference between the cast textile reinforced concrete and the printed textile reinforced concrete. This is the textile preparation process and the printing of the concrete samples. First, we got the textile from Aachen University, Germany. We cut the textile into the required size, and then we coat the textile with epoxy. After the first layer or the bottom layer of the concrete was printed, we manually place the coated textile onto the concrete, and then the fourth step is to apply a very slight pressure onto the textile to make sure the textile is well integrated into the concrete. After that, we will print the top layer of the concrete until all the printing is finished. Here are some experimental results. This figure is the comparison between the printed concrete beam and the 1 layer textile reinforced concrete beam. As we can see from this figure, by using only 1 layer of textile, both the strength and the ductility of the printed TRC beam is significantly higher than the unreinforced concrete, unreinforced printed concrete. This is when we did the test, we can see how many the deflection or the printed beam can have. This beam has 3 layers of textiles. We can see that for the TRC beam printed, which is printed, can exhibit extraordinary deflection capacity under flexile load. And also we studied how the textile layers will affect the flexile behaviors or the printed concrete beam. As we can see from this, if we increase the layer of the textiles, the flexile performance is improved, but the improvement from 1 layer to 2 layers is significant, but the difference between 2 layers and 3 layers is less significant. The reason is because of the location of the different layers of textiles. Usually, because all the textile failed because of the tensile rupture of the bottom layer of the textile, So when the bottom layer textile is ruptured, the top layer, which is 5 millimeter above from the top, the tensile capacity was not fully utilized. These three figures, I think, are very encouraging. We did some comparisons between the cast and printed TRC beams, and it's very encouraging to see that the printed TRC beams exhibit very similar flexile responses as compared to the cast beams. So it means that there is no significant influence caused by the printing process if the printing process is well controlled. Now we are going to move to the analytical part. I think this is a question we want to every structural engineer want to answer. So will the current design method for cast concrete component work for printed concrete component? Because for this case, we did some preliminary study for concrete beam. So we use the theoretical method to predict the flexile performance of the beams. And we made some basic assumptions. Actually, all these assumptions are usually adopted by structural engineers to predict the performance of cast concrete component. The first one is the plane sections remain plane after deformation. The second one is the strain compatibility exists between the textile and the concrete. The third is only the textile reinforcement in the longitudinal direction will contribute to the tensile resistance. First, the thing we have to consider is the concrete stress strain models we use in the analytical study. We use the three different concrete stress strain relationships. The first one is a typical unconfined high strength concrete stress strain model, which is as we can see from this figure, which is titled as number 1. For the second stress strain curve, which is mostly suggested by FIB code. So after the ultimate concrete stress is reached, the concrete will be able to maintain this stress until the ultimate axial strain is reached. So for stress strain curve 2, we assume the ultimate axial strain will be 0.01. Well, for stress strain curve 3, we assume this ultimate axial strain to be 0.005. For the tensile, for the textile, so we assume actually the textile can only contribute to tension, not compression. This is the principles for the numerical integration procedure. So we try to divide the whole cross section of the concrete beams into many different layers, and in different layers, if we know the neutral axis depth of this concrete beam, we are able to determine the axial strain at each layer. In this case, by using the provided concrete stress strain model and the textile stress strain model, we are able to predict the force, the stress of the concrete as well as the textile in each layer. In this case, we will be able to predict the whole flexible behavior of the concrete beams. So this is the procedure we implemented into the code. First, we input the cross-section dimensions of the concrete beam, and then we input the materials properties, and we divided the cross-section into different strips. In our study, we divide the width of each strip is 0.1 millimeter. And we set because in our study, all the failure or the specimen are caused by the failure or the textile. So we will set the bottom layer of textile, the tensile strain or the last layer of the textile as the dominating factor for this analysis. And then we assume a DN value, and then we are able to calculate the strain, stress, force, and moment for each, for both concrete and the textiles. And then, because this is for a concrete beam, if the load P equals 0, we are able to output the bending moment and the force or something. If not, we are able to go back and to change a new value for the neutral axis steps, and then we go ahead with the calculation until the P equals 0, and then we will get the final right solution. In order to validate our modeling procedure, we first did some model validations with some people's experimental work, which is for cast concrete. Based on our calculation, so our calculation for they have two different loading cases. For the first loading cases, our simulation result is 707 Newton meter per meter. For their predictions, the 715, and for this both our prediction and their prediction are slightly less than the experimental values. Same case, same conclusion for the other loading case. So based on these comparisons, we can see the prediction values are almost identical to the predicted values in their Hawkins in the 2018, and also were close to the experimental values. So our numerical integration procedure is correct. And then we did our model validating for our own test result. As we can see from these figures, I mean, from the right two figures, the top one is for cast samples and the bottom one for the printed samples. We can see the black column is for experimental result. We can see that in all the cases, the prediction results are smaller than the experimental one. The prediction value, if we are going to use the parabola rectangle model with the ultimate tensile strain of 0.01, we can get much closer result, as we can see the red columns. If we are going to use the real unconfined stress strain curve for high strength concrete, the prediction accuracy is much less. So our conclusion here is using the high, and also from these two figures, we can see that in general, the prediction accuracy is higher for the printed samples. But we cannot say so this numerical procedure works well for the printed samples, because we have only quite a limited number of samples in our case. And also we did some failure pattern predictions, and also we can see that so if we are going to use different concrete models, our prediction will give us very different failure mode predictions. If we are going to use the parabola rectangular model without ultimate tensile strain or with ultimate axial strain of 0.01, which is curve 2, we are able to predict that concrete beams will fail under tension. But if we are going to use curves 1 and 3, as we can see from the left figure, the prediction tells us the samples will fail in compression. So the assumption of the concrete as an elastic, perfectly plasticity material does provide a simplified method to predict the flexible load or printed concrete samples with a good accuracy. I will go to this the final part of this presentation. The first conclusion is the AR glass textiles has been demonstrated that it can be used as a primary reinforcement or 3D printed concrete component. If we are the printing quality are well controlled, the printed TRC beams show very similar performances to the cast concrete beams. For the analytical part, we think if the concrete quality are well controlled, existing structural design procedures can be used to predict the performance of the printed concrete components. However, the prediction accuracy is highly dependent on the concrete stress-free model we used. The last point is if we really want to achieve a fully automated process of producing concrete component, we have to think about it, the automated textile placement method in the future. That's all my presentation. Thank you so much. This is my contact details. If you have any question, please let me know. Thank you.
Thank you. Thank you very much, David. Very interesting to see that there are also some reinforcement technique that can be also applied to concrete printing. I've collected a couple of questions also for you, and we will discuss this in the roundtable discussion.